Welcome to the Belimo web series on the Belimo energy valve. Today we'll be discussing the Delta T manager and how it can save you energy. And in order to understand that, we're going to talk a little bit about coil efficiency and how managing Delta T will save energy. Let's first talk a little bit about Delta T. Delta T at the coil refers to the difference between the supply and return water temperature from your coil. When you send very cold water down to your chilled water coil, if you do not transfer enough heat, that water will remain cold and get sent back to your chiller at a colder temperature than is designed. This is what's known as a low delta T. It's inefficient for several reasons. Since we're not making the water any warmer, it means we haven't transferred that heat into the space. In order to achieve this type of low delta T, it means we have to increase our GPM. That means we're flowing water faster and not increasing any BTU output. When we do this, we obviously incur more pumping costs from pumping more water, and we reduce our overall plant efficiency. The Delta T manager adjusts the valve if the Delta T drops below the set point in order to maintain peak coil efficiency. As an example, suppose that we determine the optimum Delta T is 12 degrees Fahrenheit. And we have programmed the energy valve and the Delta T manager to not let that Delta T drop below 12 degrees F. If the valve does drop below 12 degrees F, we will see the following response. Let's take an example here. Suppose the valve is flowing 64 gallons a minute, and at this rate, we're achieving a very high amount of BTUs relative to the performance of the coil, but we're also creating a low Delta T when we do that. We can see at this point, the Delta T is just above 10 degrees Fahrenheit, and we're creating about 325,000 BTUs. With Delta T manager in place, we will restrict the flow through that valve. By restricting the flow, we'll drive the Delta T back higher, but due to the inefficient nature of coils at high flow, we see little or no reduction to the amount of load that can be delivered to this space. So again, we're still achieving in that area of 325,000 BTUs, but we're using significantly less water to do it. Let's take a look at the cost associated with controlling at those 2 points. Assuming we have these 2 points here on which we could control this coil. Point 1 uses about 55 gallons a minute and achieves 320,000 BTU. Point 2 uses about 10 gallons a minute more and achieves about 5,000 more BTUH into this space. So you can see here we have a very small increase in BTU, while percentage-wise a fairly large increase in flow. If we examine this on a chart, we can see here that it takes 18% more GPM, and it nets us just 1.6% more BTU. So then the question becomes, how much money does it cost to pump 18% more water? Well, the pump affinity law tells us that we have to cube our flow increase to calculate the horsepower increase. So that means it takes 65% more pump horsepower, or 65% more dollars, to increase our BTU by less than 2%. As you can see at the very high end of this coil curve, the last few percent of BTUs are very expensive. Let's take a look at some real-world examples where Energy Valve has been installed and Delta T management has been very successful. We will start with our first case study at MIT University in Boston. At the Hayden Library on the MIT campus, all of the air handler units were retrofit with the Belimo energy valve. The Hayden Library is a 150,000 square foot building over 3 floors, and it was built in the late 1940s. 6 air handlers were retrofit with the Belimo energy valve, and previous to Delta T management, the measured Delta T of those coils was just above 6 degrees F. From August 9th to October 9th in the year 2010, they experienced a Delta T of 6.15 prior to Delta T management. The following year, during the same time period, the Delta T was nearly doubled when using Delta T management. Dr. Gregor Henze of the University of Colorado has written an excellent field study report based around the energy valve experience at MIT. This paper was written cooperatively with Belimo and details the hydronic effects experienced in that building. It is very informative and quite technical. If you'd like a little bit of lighter reading, Belimo has also produced a 4-page case study about the MIT project. Another high-profile project that was done using the Belimo energy valve was at the University of Miami Hospital, specifically at the Rosenstiel building. At this building, there were energy valves installed on 11 air handler units that were encompassing about 2,600 tons of cooling. Previous to Delta T management, they were using over 10,000 gallons a minute to serve this 2,600 ton load, and the average Delta T was 5.5. After implementing Delta T management, the Delta T was raised from 5.5 to 10.5 degrees Fahrenheit, and the flow was reduced down to about 5,600 GPM. The performance contractor on site has estimated that there will be about a $66,000 a year savings, and the estimated simple payback on these energy valves and his services would be just under 3 years. This case study, as well as both publications regarding the MIT project, are all available at energyvalve.com. Let's take a look at one last case study. It comes to us from a large technical company in North Carolina. We have been asked not to use their name for marketing purposes, but they have been willing to share their data. What you're looking at here is a graph where we are plotting tons of cooling across the x-axis and the corresponding delta T on the y-axis. The three separate clouds of information represent three different control modes. So with the energy valve in place on a single air handler, it was run first in position control mode. Position control mode is basically a standard control valve. Each value of the control signal controls how open or closed that valve is. This would be a similar function to any characterized ball valve or globe valve that you might have in place. You can see here that the required loads were between 45 and 75 tons, and with position control mode in place, they were achieving delta T's anywhere between 5 and 7 degrees Fahrenheit. On the subsequent time span, with the same valve on the same air handler, the energy valve was switched to flow control mode. Flow control mode is a pressure-independent mode where each value of the control signal delivers a specific GPM of water to the coil. You can see here we were in similar load ranges, but now we're achieving delta T's in the neighborhood of 10 degrees Fahrenheit. On the third time period, the energy valve was switched to delta T management with flow control mode. With delta T management in place, you can see, again, we are serving the same high loads in the space, but now we're getting delta T in the 14 to 16 degree Fahrenheit range. So what does that mean in terms of real energy investment? Let's take a look at a single load point. If we examine 60 tons for each of these control modes, it will let us know what it really costs to operate each of these modes. In position control, in order to serve 60 tons of cooling at 6 degrees F, 240 gallons a minute were required. In flow control, to serve the same 60 tons near 10 degrees Fahrenheit, require almost 100 gallons a minute less water than position control. And with Delta T Manager engaged, the same 60 tons only requires 96 gallons a minute. So the difference between a standard control valve in this application and a valve with Delta T management, the flow rate was reduced from 240 gallons a minute down to 96. That's 40% of the original flow rate to serve the same amount of load in the space. To learn more about the energy valve and other features available, please go to www.energyvalve.com or reach out to your local Belimo representative or distributor. And please feel free to check out another one of our web series on the Belimo Energy Valve.